What if everything we thought we understood about the birth of the universe is starting to unravel? Nobel Prize-winning scientists are now grappling with findings that suggest something is fundamentally amiss with our cosmic assumptions. This shift has been sparked by startling new data from NASA's James Webb Space Telescope, a $10 billion observatory launched with the goal of exploring the universe's earliest epochs. Not long after it began operations, the telescope started delivering observations that no one had predicted, a universe behaving in ways that challenge the very core of modern cosmological theory. Just months into its mission, the James Webb Space Telescope JWST stunned cosmologists with unexpected discoveries. It detected galaxies so massive, luminous, and evolved that, according to current models, they simply shouldn't exist so early in the universe's history. The prevailing understanding suggests that such structures require billions of years to form. Yet JWST was seeing them a mere few hundred million years after the Big Bang. One of the foremost voices acknowledging this upheaval is Nobel laureate Adam Rees, whose own work helped uncover the accelerating expansion of the universe. He now says there's a real and exciting possibility that we may have profoundly misunderstood the cosmos. What JWST captured during its observations of the so-called cosmic dawn, the era when the first galaxies formed, is forcing scientists to reevaluate decades of accepted theory. The telescope spotted fully formed star-filled galaxies existing just 300 million years after the Big Bang, a period considered almost impossibly early for such complexity. One particularly striking example is a galaxy labeled JD's GS Z14-0. It was seen at a redshift of 14.3, meaning we're observing it as it was only about 290 million years after the universe began. This galaxy isn't a faint smudge. It stretches over 1,600 light-years and is actively forming stars at a furious rate. As one researcher put it, it's astonishing that a galaxy of this scale could appear so soon after the cosmic clock started ticking. But this isn't a one-off anomaly. JWST has uncovered a multitude of galaxies from that same early era, and they're breaking all the rules. They're too mature, displaying intricate structures that should take billions of years to develop. They're too bright, shining with the combined light of billions of stars that shouldn't yet exist. And they're too organized. Not chaotic and diffuse as expected, but instead well-formed with features like disks and even central bars, the kind typically found in much older galaxies. In fact, between half and 80% of these early galaxies are elongated and flat, more like surfboards than the spherical blobs scientists predicted. It's as if we were expecting to find microbes in Earth's primordial oceans and instead encountered dolphins. These revelations have not only surprised astronomers but have posed a direct threat to the standard model of cosmology, the lambda cold dark matter, lambda CDM model. This framework has long suggested that cosmic structure forms slowly, beginning with small blobs of matter that gradually merge into galaxies over billions of years. But JWST's findings contradict this, revealing a young universe already teeming with complex, massive galaxies. Alison Kirkpatrick, an astronomer at the University of Kansas, summed up the crisis. Everything is simply too big, too soon. This mismatch between theoretical predictions and observational data is so significant that it's kept some scientists awake at night, wondering if the foundation of their understanding might be fundamentally flawed. This isn't a case of minor miscalculations. These findings are pushing cosmologists into what many are calling a crisis. The data has been checked and rechecked, it's real, and the instruments are working exactly as they should. The Atlantic even reported that JWST's early observations forced researchers to confront the possibility that their long-standing models may no longer be valid. Some experts initially suspected calibration issues, but those were ruled out. What remains is the undeniable evidence, a young universe that contradicts our established understanding of how galaxies and cosmic structures came to be. Even more dramatic are the responses from some of the very scientists who helped build these models. Dr. John Mather, a Nobel Prize-winning physicist who was instrumental in designing JWST and in measuring the cosmic microwave background, the Big Bang's afterglow, has acknowledged the surprises. He noted that the galaxies JWST is uncovering are not quite like what we thought they were, describing them as unexpectedly large, luminous, and abundant. Coming from someone at the very heart of both the Big Bang research and JWST's design, this admission carries enormous weight. Adam Rees, another Nobel laureate, led a JWST project aimed at resolving what's known as the Hubble tension, a discrepancy in the measured rate at which the universe is expanding. Instead of resolving it, JWST deepened the mystery. Its high-precision data confirmed the faster local expansion rate, ruling out errors in previous measurements. Rees responded by suggesting that we may be facing a real possibility that the underlying physics of the universe itself is being misunderstood. He pointedly asked whether we truly grasp what the universe is made of or how its laws operate. Then there's Sir Roger Penrose, a Nobel-winning mathematical physicist known for his work on black holes. He views the JWST findings through the lens of his own less conventional theory, conformal cyclic cosmology, which posits that our Big Bang was just one phase in an eternal sequence of universes. According to Penrose, the surprising maturity of these early galaxies could be remnants from a previous cosmic cycle. While speculative and outside mainstream science, his interpretation highlights the degree to which these results are prompting radical reconsideration even among the field's most respected figures. Despite the shock, many experts view this disruption as a rare opportunity. Instead of seeing it as a problem, they see a chance to rethink and perhaps greatly expand our understanding of the universe. As Rees emphasized, these aren't challenges to be feared, but rather doors to discovery. Yet, the surprises didn't end with galaxies. JWST also brought fresh urgency to the Hubble tension, one of modern cosmology's biggest unresolved issues. For years, scientists have measured the universe's expansion rate in two different ways. Measurements using nearby supernovae and Cepheid variable stars suggest an expansion rate of about 73 kilometers per second per megaparsec. But calculations based on the cosmic microwave background yield a slower rate, around 67. That 9% difference may seem small, but it's far beyond acceptable error margins in precision cosmology. JWST was expected to settle the debate by refining these measurements, but instead it confirmed the faster expansion rate with even greater clarity. By resolving individual Cepheid stars in galaxies that Hubble couldn't see clearly, JWST ruled out instrument error and cemented the tension as a genuine problem. Rees stated plainly that this result increases the mystery and raises the likelihood that we may need to introduce entirely new physics into our models, perhaps a form of dark energy that changes over time, or unknown interactions with matter. Some researchers have speculated that these findings could even suggest a previously unrecognized form of energy that accelerated the universe's early growth, or indicate that gravity itself may behave differently on large scales than we currently assume. These possibilities, while still under study, point to how fundamental the issues have become. Meanwhile, another piece of the puzzle emerged that changed how scientists interpret JWST's findings. A research team led by Stephen Finkelstein reassessed some of the supposedly enormous galaxies JWST detected and made a striking discovery. Many of these galaxies weren't quite as massive as they first appeared. The reason? Supermassive black holes. These active black holes at the centers of young galaxies, known as quasars, can emit so much energy that they make their galaxies seem far brighter and more massive in infrared images than they really are. Once the researchers accounted for the light emitted by these black holes, the inferred mass of some early galaxies dropped significantly, in some cases by half, bringing them more in line with what models predict. However, while this correction solves part of the mystery, it introduces another. These black holes themselves are a puzzle. How could such massive black holes, weighing millions or even billions of times more than our Sun, form so quickly after the Big Bang? That question has opened a new frontier of research, even as it helps narrow others. Even with these black hole adjustments, JWST is still seeing more early galaxies than expected. The rate at which galaxies formed in the universe's early days still seems to exceed what current models can explain. This has pushed scientists to reconsider other assumptions, such as how quickly stars could form in the early universe, how dark matter clumped together in those early years, or whether feedback mechanisms from the first stars and black holes operated differently than we think. Some researchers are even contemplating changes to the nature of dark matter, or gravity itself, to explain the observations. Despite the growing list of anomalies, no one is abandoning the Big Bang theory. What's happening instead is a refinement of the models that describe what happened afterward, how galaxies formed, how matter behaved, and how cosmic expansion evolved. Scientists are investigating a range of potential solutions,